Hello, everybody. Hope everybody can hear me. My name is Salvatore Di Bernardo. I'm a member of IABSE, part of also the US group. We are here today for a webinar organized by IABSE, the International Association for Bridge and Structural Engineering. This webinar will be covering bridge collapses and also lesson learned from those collapses, because that's the most important thing. When something happens, how do we avoid the next one from happening? The webinar is organized by the IABSE Commission 1, Performance and Requirements, and also the US group of IABSE. You see the presenter here on the slide, and also Maria Pina Limongelli, who is the force behind this Commission 1, and also this is the first of a series of webinars that we call the Duo webinars, which the intent is to combine academia and practitioners together to share their views of a topic. So this is the first one. We hope this will be the first of a long series, and we're always open to any recommendation and suggestion that you have about topics. I want to say a few words about IABSE. I know there will be members, people that are already members and know a lot about this association, and I hope there is also some new people that maybe are coming in touch with IABSE for the first time. So the mission of the association is to exchange knowledge and advance the practice of the structural engineering worldwide. So there is, we cover all aspects of structural engineering, bridges and buildings and special structures. We count 2,500 members in 100 countries. And this is kind of the uniqueness of this association. It's like a very, very international group of people. One of the highlights, some of the highlights of what IABSE does, definitely like publications are very important component of the activity. There is a magazine, Structural Engineering International, which published monthly and collects scientific and technical paper from all over the world. And also we have the green books that are more like focus on topics of structural engineering, and they go very much in the detail of that. It's almost like design guides that people can use all over the world. And then we publish also bulletins. One of the organization of the group is divided in task groups and national groups. Task groups are mostly by topic, and they've been, to say that in the recent year, they've been becoming even more active, and there is always like a need and a willingness to have more people join. And then since the nature of the group is international, we also are organizing national groups, and national groups do the activities on their own, in addition to the overall activity of the association. The main purpose is to organize seminars and conferences. As you can see here, this is just like a short summary of like a few conference that we had in the recent past. So you can see from this slide that we've been covering pretty much the entire world with like location of conferences, and the participation is really very, very international. So these are like a few things about technical commission. We have 6 technical commission: performance and requirement, conceptual design, structural analysis and evaluation, construction methods and processes, existing structure, and sustainability. And then we also have more specifically and more focused group called task groups, and we are around 45 of them. So events, like I said before, are the main focus of our association. The upcoming ones are like Prague in 2022, both in 2022. In May, we have a symposium in Prague, and then the main event will be the Congress that we have every year. We have one main event in the fall. Normally it's the Congress, and this time will be in Nanjing in 2022 in China. As we all know, we've been through COVID, so there is a lot of e-learning and webinars right now, but we hope we can get to be in person again soon. One thing I want to highlight, we are very open to young engineers, and there is like some advantages on joining when you're like, we define young, I believe, below the age of 35. So there is like pricing is more affordable for like younger members, and there is also like a younger engineer group that is very active. Plus, we also have at the national group level young engineer activities. So definitely, I will. If you're not a member, I will encourage you to take a look at what IABSE offer. Consider becoming a member. And then one thing I want to point out about the webinar today, we will provide continuing education credit. So you can get 1 hour of continuing education, like a certificate or PDH, like they're calling them, we call them in the United States. If you are interested in receiving a certificate, send an email to Brindarik@Bose. The email address is here, and you will receive it in a timely fashion. With that, I think I'm going to pass it to Maria Pina to introduce the webinar.
Thank you, Salvatore, for this very comprehensive description of the IABSE activities. I would like to focus on these Duo-IABSE webinars. These webinars, this is the first one of, we hope, a long series, and they come from an initiative of Task Group 1.9 of Commission 1. And the idea is to provide a forum for the presentation of and the discussion mainly of interesting and hot topics in the field of bridge and structural engineering. The idea of these webinars, the Duo name, comes from the idea that an academic and the practitioner present and discuss the theme of the webinar from two different perspectives. And at the end of the presentations, we will have a question and answer session where you all can ask questions through the question and answers function. Do not use the chat, you have to use the question and answer, and Salvatore and I will moderate the discussion through your questions. So the first of these webinars, as you all know, is about bridge collapses, and we want to tackle this topic from the perspective of the lesson learned. Of course, which bridge collapses are shocking events, and in some cases they lead to huge tragedies, especially if they involve human losses. But we can also learn from these tragedies, and we will see in a couple of minutes what we can learn, at least from the perspective of our speakers. But before starting with the webinar, I would like to inform you about another initiative that has been started in Commission 1, specifically in Task Group 1.5, which is the collection of a database of bridge collapses. We have now almost 1,000, actually there are 850 cases of bridge collapses, which are described in this database. And we would like to widen this set of bridges. And so the idea is that what I would like to do is to ask you to contribute. And you can go ahead, Salvatore. To contribute is very easy, it's very straightforward. There is a web page in the IABSE website, the web page of Task Group 1.5, where you find the description on how to contribute. And if you contribute, you will be awarded with the database. You will have access to the database. So this is was the information that I wanted to to give you and to ask to contribute. Now back to our webinar, back to today. As I said, we have the topic today is bridge collapses. What can we learn from this event? And in this logic, in the logic of the Duo webinars, we will have an academic who is Professor Camillo Nuti, and who will be the first speaker, and a practitioner, Dr. John McGormley. And as I said, the question and answer session will follow. I will not say more about this topic. I will leave the floor to the two speakers. I want just to remind you that the webinar is being recorded, and it will be available later in the IABSE website in the section of IABSE e-learning events. Now, I will leave the floor to Professor Camillo Nuti, who is full professor at Roma Tre University in Italy. And he was a member of the technical commission, which was appointed by the government, the Italian government, immediately after the collapse of the Polcevera Bridge. And he followed in detail all the investigations in the first month after the event. So it's my pleasure to leave the floor to Professor Camillo Nuti, please.
Hello.
You can share your presentation.
Yes.
Probably Salvatore has to close the sharing, maybe.
I think so. I should appear on the screen, maybe.
I did. You should have a green square where it says share the screen. In
it's
the
all
bottom
yours,
of
Camillo. I'm
okay.
out.
Yes.
Perfect.
Okay. Good morning. First of all, let me acknowledge my co-author. There are many, and I must thank some, like Professor Briseghella from Fuzhou University, Professor Quaranta from La Sapienza, Professor Dezzi from Ancona, Professor Vanzi from Pescara, and others around Italy. But let me first thank IABSE for inviting me to give this presentation, and Maria Pina, who thought to me. And as Maria Pina told to you, I was involved in this terrible event, was the failure of the Morandi Bridge in Genova. The Morandi Bridge existed since 1964, let's say inaugurated in 1967, and then failed, unfortunately, in 2018. And then there were something after, and the bridge has been rebuilt recently in less than 2 years. And there are a lot of activities ongoing, thanks, unfortunately, to this event. Like after a war, people think what's happened. So let me enter in I don't know why this doesn't disappear. And let me enter in my presentation. This is the outline. Let's first the presentation of the situation in Italy of roads, bridges, etc. Then the Polcevera Bridge. What was the monitoring of the bridge in more than 30 years and the outcome of the inspection commission. Then the impact in Italy on public and technicians and politicians. Then failure statistics all over the world. Then the bridge reconstruction and what is going on in Italy after part of the reconstruction. So the guidelines and all the operations and things that happens. And finally, the conclusions, some conclusions. So the bridge in Italy, as you can see here, we have a lot of bridge in Italy, more than 40,000 important bridge and more than 60,000 kilometers of statal roads. but then is just the 4% of the total amount of the stock of bridges and of roads, and we only know 10% of those infrastructure in detail. And what about the rest? And then there are the railways, bridge, and which are 20,000. And but what does it mean that we know them? In fact, the Morandi Bridge was one of the most important bridge in Italy, and they fell down. This is the Morandi Bridge. It was there for more than 30 years, from 67 to 2018, quite 50 years. And then in August 2018, this happened. It was terrible. 200 meters of the bridge came down. You can see here, Pier 9, while Pier 10 and 11, they just stands. And unfortunately, but why they didn't fail? Probably because in 1993, they were retrofitted while this part was not retrofitted. Then the cables, the stays were partly reconstructed for Pier 11, not for Pier 10, just a little retrofitting with some jacket. After the failure, the government established this commission. I was part. There was 3 from the ministry and then 2 professors, Professor Vanzi and myself. And the ministry asked to the management firm of the highway to give us available all the documentation about the construction and maintenance, and then all the data about the possible reconstruction of the incident. And in 1 month, based on those documents, we provided the report that the ministry published immediately, so it is available. And the conclusions are the control procedure were essentially inspection. They are unsuitable to prevent collapse and insufficient for estimating safety, and the risk of collapse of the bridge would have emerged through an assessment which was mandatory by before 2013 based on Italian regulation. And then corrosion evolved in the last 27 years very much. There was the deterioration check was carried periodically based on qualitative investigation, essentially, and non-destructive test. The surveys was able to qualitatively grasp the temporal evolution of the deterioration. The time of exposure to corrosion was sufficient to determine the breakage of some cables, on many, we don't know how many. The inspection was not extended to all the cables, and not prudential provision were taken. The project in 2017 for intervention on stays of Pier 9, and on the buffer deck showed that the shear and bending check were not satisfied. Then there are other points like the sequence of failure, the works for the new inspection under bridge unit, and an hypothesis on failure, and a check of the few structural intervention in 20 years. Then, which kind of monitoring had been done on the bridge in about 30 years, from 1990 to 2018? The Italian code for inspection was based, as a monitoring was essentially based on visual inspection and non-destructive tests, essentially visual. Every 3 months, there is a qualified personnel that must be that make an inspection, and every year an engineer must go there, and then there must be a report for every inspection and a sheet on every bridge. And Autostrade, the owner, let's say the owner, those who manage the bridge, had a very detailed manual for inspection. As you can see here, they give score to the different type of deterioration, very detailed, all based essentially on inspection, but also on some investigation, which has been carried out on on Polcevera Bridge, on Morandi Bridge, inspective, then reflectometric impulse measurement technology, the RIMT, from 1996 to 2017, then sclerometric test, pull-out test, ultrasonics, extensimetric measurement, and finally, two dynamic identification in 1996 and 2017. You can see the results of the inspection in the 90s, and then what I could see is that the stays at the top of Pier 11 was very deteriorated. They lack of injection, and there were also some breakage, and there was pitting and diffuse corrosion. Therefore, in 1993, there was a strong intervention on Pier 11 with the substitution of stays, and on Pier 10 with a jacket of the top part, not on Pier 9, unfortunately. And then in the remaining here, as you can see, I don't know why I cannot. In the remaining here, there was also some other testing 2000, from 2000, let's say from the 2000 to 2018, some others on the stays, and the concrete was in very good shape, while the cables, the steel was not in a very good situation, with pitting corrosion, and also strain gauge tests at the beginning in the 90s, until the 90s, and then into 2000s were done, and they they continued to show that the concrete was in good shape, but the steel was so and so. And then, okay, we can go on. And then the reflectometric rim test, they show that there were problems on Pier 11 very much, but in the 2000, every year there was a test on one side 1 year and the other in the other year, and they showed that there was a progressive degradation of the situation. But this was not a big alarm. They just thought to make some design. The dynamic test for the commission, they didn't show nothing, especially they are something that show you the global behavior, not the very local one, which is needed for corrosion. And then there were also tests on the decks, the simply supported deck, and in the 90s they were reinforced with some jacketing, but in the year in the 2000, after 2000, they showed to have some important problem. With a visual investigation, they checked that there was some breakage here at the attachment with the old beam, and then they did some a reflectometric investigation on the cable that showed that there was a progressive worsening of the reinforcement and also of the new concrete put. And then these are the sheet of the inspection. When the score is larger than 50, it is very dangerous. It should be, they should give an alarm, and there were some with 60, but some were underestimated, like here. We have not the time to enter, but these are the picture 2011, 2013, and one can see that there is an evolution, very dangerous, that the corrosion was going on fast. And the breakage was 5 centimeters in 2011 and 6 in 2013. So it's very dangerous situation. And the rim test again showed that there was problem both on corrosion and in injection. Then we had a failure, and the failure is terrible, but we have the confirmation that there is corrosion. This is the east with the attachment of the underbridge unit ongoing. They were doing these new works, and they were putting these bolts, one every few centimeters, and there are a lot of stirrups here, but there was no check of the interference of the bolt with the old steel. So this is an additional problem, the lack of accurate check of the work to the opinion of the commission, and then the east and west. So you can see here pitting corrosion in the cables, the output, immediate impact in Italy, public opinion. Are we safe when we go on the highway? And the engineers, which are the causes? Is this an Italian international problem? What can we do? Are we at the edge of a disaster due to time from construction? The largest part of the infrastructure in Italy, let's say more than 50%, have been built after the Second World War. So they have about 40, 50 years. Do we need a code for existing bridges? What we should do for this case? And then the architect, they also discussed, shall we maintain or not such masterpieces? The reconstruction should include landscape consideration and urban redesign. And the government, they ask how we manage the highway infrastructure and what about the money? And then we had some first outcome where the discussion and the outcome were in the media for public opinion. For the engineer, they told that we need studies, courses on corrosion, studies on corrosion, and it is not an Italian problem, but it's a general problem. And what can we do to prevent? This is still an open issue because of the ignorance on corrosion. Are we at the edge of the disaster due to time from construction? This is again an open issue, but we can be quite positive now. Do we need a code for existing bridge? And we have now. What we should do for this specific case, a fast reconstruction? We need money, then we need sensors. And the architect, they did a lot of workshop and intervention, and the government, they act immediately with a law for reconstruction, with a new code for existing bridges, and put immediately 200 million for reconstructions and for co-tuning and inspections. Then the statistics on collapses show, as you can see here, that this is a PhD study, that the failure are all over the world, not only in Italy, but all over Europe, all over United States. And so it is, and we don't know what's happened in Africa because we don't have enough data for Africa, but in all the developed country, we have failure. So there is a problem. And why? Many during construction, but many other after construction. And why they collapse. And you can see here, from 2% to 10% cases are due to deterioration, but the greatest part is due to floods. And this is confirmed also by a report by Parsons and Brinkerhoff in 2003, when you can see that for them, in the 13% of the cases, the need for investigation was given by the state of deterioration. And also, this is a confirmation. And again, when it is another study during construction, but after some time, we have failure after 5 years. And so again, here, another investigation show that around 5% of the cases are due to deterioration. So we can conclude, and this is a Chinese study, that corrosion is increasingly present as the cause of the crisis. We have now a critical time for bridges built after the Second World War. We have not developed a case study to generalize knowledge. We need to work on. We must always adopt a so-called precautionary principle because of our known ignorance on the subject. Well, the bridge has been reconstructed out of the failure. We have the commission and the government decided that the bridge should have been rebuilt. They give the mayor of Genova the power and the money to rebuild the bridge, and they establish a competition for ideas and proposal that ended in 2019, and they decided at the end to reconstruct the bridge where it was on the same line, demolishing the old bridge, though there were alternative proposals. And this in part is due to the Piano, using an artist star living in Genoa idea of a straight bridge. You can see here the proposal up in the upper part, the straight bridges proposal. There was only one. I am honored to have worked on that one, of a curved double-deck girder bridge, which eliminated the need of demolishing the bridge. You can see it here. There is also a movie for those ones, but there was other interesting proposal. But as they were all straight bridges, they had the need of demolish the bridge. And this was done in 2019, just after giving the work to the group of Fincantieri, Salini, and Italfer, and that in the August 2020, they inaugurated the bridge with a lot of sensors inside. I don't know if the sensor whatever is needed by, but this is a good point. Now there are new guidelines. We understood that there is a need, and the government understood, so the engineer win in that sense. There is a need for guidelines for risk classification and management, the assessment of safety and monitoring of existing bridges. The guidelines have been set up in 2020. In December 2020, they became a code for Italy, and the government gave funds for studies and to tune the guidelines. This is very important, involving all the university and not only in Italy. I just show you one of the cases. There is a bridge, a real bridge, which is out of use now on the highway in the south of Italy. This is the longitudinal and transverse section, and this is a picture of the bridge with the phases, and these are the 7 universities involved with the coordination of Trento, and there are Roma Tre University, but also others. You see that's other important university, and many kind of tests: rim, tomography, corrosion, X-ray, imposes displacement, acoustic, emission, digital image correlation, tension release, ultrasonic, and we compare the results. Here are the picture of some of the test during the test. The tests are going on, the X-ray, and here we are going now to compare the blind result that we had between X-ray, rimmed, and tomography in order to find the position of the voids in the ejection, which is one of the main problem in the cable. You have kilometers of cables in a very simple deck, even of 40 meters. You have kilometers of cable, so you cannot lose a lot of time and money. But you need to find the places. And again, you can find corrosion, but again, this is the comparison between what we can find with rim test and potential of corrosion test. And we are again comparing the results. And but there are other things that are ongoing now, because there is a general data acquisition in the ministry on all the infrastructures, and there is a big group of engineers going on in the ministry for checking and having the control of the safety assurance of the bridges in Italy. So there is a large movement, but there are some researchers now starting from the chloride present on the surface of concrete. We can study numerically the situation, taking into account of the different type of corrosion that you can have and find, with some uncertainty, obviously, of the, let's say, about 30 to 50% of the uncertainty about corrosion. You can see here, for example, that in a pier, I don't have the time to enter, you can read the paper if you want, that after, in this case, it is a typical case in Italy, not far from the coast, from the sea, within 1 kilometer, let's say, then you can totally lose, even well designed, your stirrup. This is the violet are the stirrups, you can lose them. Because after 6 years, you have just 20% of the area because of pitting corrosion. And also the different type of corrosion in the different places of a rebar. Near the stirrups, you have larger corrosion than within the stirrups. For example, here you can see that in that case, after 40 years, for the longitudinal rebars 24 or 20 millimeters of diameter, the diameter, the ratio between the stirrups position and in the middle, you lose the 20% of the relative area. So, and if you go on at the end, near the stirrups, you have very small sections, and this causes possible buckling of the rebars, which can be a big problem. So we are working to propose some hazard map like we have for seismic situation. So we can set up some chloride maps useful to make analysis. And again, there's exist, but they are not enough reliable as they are not done for this scope. And you can also make evaluation of bridges, but I just send you to the publication to understand the problem. I would just comment that all the comments are very important, but what is important to understand is that the government, they are very sensible to public opinion, especially in the immediate after an event. They don't ask in detail your opinion immediately after the event. They just listen to public opinion and the big issues. So we must be prepared and be in the general discussion to have an influence on political, this immediate decision about, for example, reconstruction. But at the end, the government with the medium term, they heard and listened to the engineer. And so it was a good thing. Finally, the most important of the outcome, I think, is number 3. There are many important positive outcomes, even from a failure, that should be put to public attention. But for engineers, we must think that we are not used to discuss ideas, because we usually consider and discuss about what has been built and not about design proposal. This is very bad, because a number of innovative issues are out of any consideration in the engineer community. So we need to discuss to find an agreement on new and innovative solutions. For example, what about USPC, ultra high performance concrete? There is no debate enough, though in various cases it could help to reduce carbon emission and increase durability of structure. Finally, to conclude, I would say that failure of bridges has a large impact on public opinion. Engineers should debate themes of general interest to get a role on leading decision. There is a need of knowledge on corrosion development and monitoring techniques. The application of new techniques in comparison of results show very promising outcomes. Italy is pushing in the direction of application of new techniques to prolong service life of existing bridges with adequate safety. This is in line with the new needs for reducing carbon emission, and new tools are in development for corrosion hazard description and for the evaluation of bridge structural behavior in aggressive environment. And with this, I thank you very much for your nice attention, and question are welcome.
Thank you very much, Camillo. There are some questions already in the Q&A, but we will leave the discussion to the end as we decided. And now I would like to introduce our second speaker, Engineer John McGormley. John is a principal at Janney Elstner Associates in the US. He has been involved in multiple bridge failure investigations with a particular emphasis on fatigue and fracture issues. And recently he has been elected member of the IABSE Executive Committee and chair of the US group of IABSE. Please, John, the floor is yours.
Thank you very much, Maria. Oops. My screen visible?
Yeah.
Yes, perfect.
Okay, excellent. Well, good day, good evening, and I guess good morning, especially in the US for those of us here. I appreciate the opportunity to speak and the invitation for Commission 1. This is, as Maria Pina introduced me, this is a topic I've been working on for many years at Janney Elstner. So again, thanks to both Salvatore and Maria Pina for the invitation and the opportunity to also speak alongside Professor Nuti. So my topic today will be lessons learned from catastrophic bridge failures in the US, and that's generally covers from about 1968 is the point where we'll talk about why that's the case to the present day. And I think you'll see that there's a lot of commonalities in what Professor Nuti indicated as reasons why we have these failures and what we can do and the lessons learned about them. So kind of to bookend this presentation in terms of a time frame, we have a major failure that occurred in 1968. And then as most recently, we had it wasn't a failure or a collapse, but it was a major fracture that occurred in a bridge in Tennessee across the Mississippi River outside of Memphis, or in downtown Memphis. And as if you recall on the opening screen, it's that asterisk indicated major, either deaths or tragic loss of life or injuries, but also economic impact, and is noted in the newspaper headline to the on the right. There was a big economic impact. So with these two kind of losses in terms of structural problems, defining the time period, we'll talk a little bit about that. So the 1968 Silver Bridge was really a milestone event in the US for bridges. The structure itself was an I-bar suspension bridge. So it was a chain of steel links together and across the Ohio River down between Point Pleasant, West Virginia and Gallipolis, Ohio. So it was a long bridge, and the steel was a high strength steel at the time. On December 15th, 1967, while under a vehicle loading, the structure collapsed. And it was really a result of some stress corrosion cracking that occurred in the I-bar chain. And it was a non-redundant structure, meaning that should one of those elements fail, there was not a load path to support the loads, an alternate load path to support the loads. And so the structure collapsed. Out of this tragedy came some major changes in the way the US practices its bridge management. And so what were some of those improvements? Well, first, we started to require inspections of bridges. So all public roads that had bridges on them required inspection biannually every 2 years. And then later, as we start to define risk, we've changed that, but initially it was every bridge needed to be inspected. We also started to look at the importance of fracture critical members, or those as members, as I said, that should they fail, lead to the collapse of the structure. And then we also looked at, through material toughness requirements and detailing and welding procedures and fabrication requirements, improvements in how we would construct a steel bridge. And so those happened later in the 70s and into the 80s. So from that point on, we've been operating under, for the most part, the same regulations and procedures. There's been tweaks, and based on studies that have been done through the Federal Highway Administration, we've improved our inspection requirements for inspectors and looked at opportunities to improve it. But generally, we've been operating since 1968 under these requirements. Then in May of this current year, during an inspection, inspectors found a very large crack in a fracture critical member on a bridge. And this is the one in Memphis. It's a little misleading in this photo in the sense that this is a box-shaped member that you see in the crack in front of you. And so the web member, or the vertical member that is fractured, has a equal size member on the other side of the photo, which has remained intact, as did a portion of the bottom plate. So it wasn't a complete fracture, but it was one of those fractures that should have gone all the way through. It would have been a considerable amount of problems with the structure stability, maybe have even led to its failure. So it was, and we'll talk a little bit about this towards the end of the presentation, but again, it pointed to the impacts that a failure, or at least even in this case, a fracture can have on the economy. So it was closed for 3 months and then reopened in August. So as typical, and I can swap out different headlines for different bridge failures, but I just pulled the one from the Memphis one. Is, immediately there's criticisms of what we're doing in the bridge practice and in the design practice for maintenance. And in this case, there was probably some deserved criticism in that these were some errors in detecting this crack in that Memphis bridge. And then, as always, there's calls for more funding, even though we may not even know why, in this case, this fracture was even caused by it, but we need to do more, is always what's called out. So we take a look a bit at some different bridges, and I've grouped 6 structures here. They kind of, they encompass a multitude of types of failures. And so the purpose is to hit these as highlights. Each one of these bridges has an extensive study that went into them, and an investigation and reports. But the idea here is just to kind of hit generally information about them, given the time frame we have this morning. But they highlight the different either structure types and the mechanisms by which we've had these failures. So I'll walk through these and kind of sum up what this tells us based off of these selected failures. So the first one we'll talk about in chronological order is the June 1983 failure of the Mianus River Bridge in Greenwich, Connecticut. So this structure had a span that crossed the river that was connected at the 2-girder system with a pin and hanger type system. And so that meant that there was, this allowed for the span to move under thermal loading, and but allowed the whole total support was through these pins and hangers. And as a result of the failure, the span dropped into the river, and vehicles traveling over the bridge fell into the river, resulting in the deaths. So what was the cause? Well, if you can see kind of blown up in the photos, those were the hangers. And what apparently happened over time was that they had done some repair work on the bridge, or some maintenance work, and had done an overlay on the bridge deck. And in the process of doing that, had covered up the deck drains with the asphalt overlay. And so in order for the moisture or the water to get off the bridge, it flowed towards the expansion joints, which happened to be the same location where the hangars were below those expansion joints. So over time, those expansion joints were exposed to de-icing salts from the runoff and caused the hangars, which are in pairs on either side of a pin, to one of them to eventually push off the pin. So the rust jacking pushed the hanger off the pin, leading to that hanger no longer being functioning. And so that left all the load to be taken by the remaining hanger. And then over time, due to the corrosion and pitting, this led to a fatigue problem in the hanger and eventual fracture, which then dropped the span in the river when that happened. So one can conclude that the Miami River collapsed due to corrosion of the hanger bar caused by poor maintenance of the structure. If I move on to another structure that happened a couple years later, this was the Schoharie Creek Bridge in upstate New York. So this bridge was affected, as you can see in the photo, during a high water event. And in the photo you see, this is the second photographer captured the next portion of the span collapsing, but the span had already collapsed in front of it, leading to 10 fatalities as they again drove over the bridge without a span there. Just to get you a little bit of a visual layout, there was piers 1 through 4, and piers 2 and 3 are now in the water during this high water event. A typical cross section through at the bridge piers. So you have a foundation element that supports some columns, and then a 2-girder bridge system up above. And so during the process of recovery, we were able to dewater the site, and eventually after the waters went down, and we were able to observe the foundations at Pier 3, which you can see appears to have a long scour length and led to a fracture in the footing. So this bridge collapsed when the Pier 3 foundation failed as a result of extensive undermining during scour. So again, an event, a high water event led to the scour and then to its failure. Now, if you take a structure like this, which was under construction in 1995 across the Tennessee River in Tennessee, outside of the little town of Clifton, Tennessee. This one resulted in 1 fatality and a couple injuries. So this was under construction, as I said, and the contractor was building a 3-girder deep plate girders, 14-foot deep across the river, and they were using a system with, shown in a clip of a video. They were using a big ringer, a big stiff leg derrick crane to essentially fabricate 2 sets of girders, put the cross frames in, and lift that unit up. Then they'd use another big crane to carry the heavier section pier girder sections across to the opposing pier. And so if I get to the day that this structure collapsed, you can see that the structure had essentially been made it to the Pier 15, and they had put in all 3 girders at that time. So they had the 2 girders in with all the cross frames, and they had put in the 3rd girder, but they had some difficulty with the getting the rest of the cross frames due to some fabrication errors, in the sense that bolt holes weren't lining up, and there was some other alignment problems. And so on the morning of the collapse, you can see that there was a barge there, and on the far left, you see a cross frame hanging from the crane. And so when that morning, they were working on removing that cross frame because you could see that it looks like a triangle, but in reality, or when installed, there's arms that fold up to make horizontal members, and those are currently folded down. And so they were in the process of removing that cross frame because it had buckled some arms earlier in the process of doing the erection, and so they wanted to fix that before they moved on. You can see that also that it's on a very relatively light line, so it was not in the structure at the time. It was loose, or otherwise it would have probably pulled the crane into the water. Unfortunately, as most times with these events, there's stories behind these. And this one, the superintendent, or I should say the ironworker foreman, he had gone home for the weekend with the rest of the crew, and had been injured on his farm. And so he didn't make it back. The crews came in on Monday, and the barge superintendent, who was normally working with the foreman up above on the steel, remained working down below and calling the shots, and had decided at that point to remove the cross frame, as I talked about. Didn't realize, though, that there had been numerous problems connecting the third girder here with the box of the two girders that had already been framed. So there was numerous cross frames installed, but they hadn't been fully bolted, or even bolted in some cases at all. They just were hung up there with some erection bolts. And so unfortunately, with that removal of the cross frame, we ended up with the failure. So after a thorough investigation, the collapse occurred. The bridge failed due to a lateral instability of the girder G1, which is the third girder, created by the removal of the cross frame. So again, an error during construction caused this problem. I moved to another structure that collapsed in 2007, and this one, the investigation in terms of the collapse was pretty straightforward. What you had was a major arterial connection here with connectors from I-80. This is in Oakland, California, and I-580 coming together in a bunch of connecting ramps and roadways. It led to the fire. So the inset photo shows the collapsed structure and how it affected both I-80 and I-580, as well as I-880, which was another connector. So what happened? Well, during the early morning hours, a truck driver loaded with gasoline was going down the interstate, went a little too fast into the curve, lost control, and spilled his truck, which ignited, releasing a fire, and it burned, unfortunately, underneath the I-580 connector. Just a bad placement of the accident. But the fires of 8,600 gallons of fuel caused the structure to collapse, and a big fire there. Temperatures got to about 3,000 degrees, which affected the steel stability and its ability to carry the supporting structure, leading to the collapse. So this, again, nobody died. The truck driver was able to survive, but it had a huge impact on the interstate in that location, with about 35,000 cars a day using the I-880 and about 45,000 cars a day using I-580. So they both were closed until they could be repaired. And so you can see again another photo of the damage that occurred and the heat effects of the fire. So again, the conclusion was pretty straightforward. It was due to a collapse as a result of a tanker fire below. The I-80 corridor, there where the yellow semi-truck is driving, was able to be reopened in 8 days. And the I-580, which was the structure that collapsed, was reopened 25 days later. But you can see the need to do that given the traffic. Now I look at a structure that collapsed again in 2007, and that was one, and maybe many of you are familiar with this project. This bridge failure was in August of 2007, led to 13 fatalities and about 145 injuries. So this was the deck truss bridge across the Mississippi River in downtown Minneapolis. It was built in 1967. It was a riveted structure, mostly made up of box-shaped sections. But as with a truss, it's connected with gusset plates at each of the nodes. A photo there kind of shows it before it was involved in the accident. And these next series of slides, as we now, as investigators to these collapses, it seems like, fortunately, with the aid of videos and phones and everything else that's out there, we can usually almost always capture some portion of a failure, even as far back as 1995. We had some videos on the old VHS tapes and at Tennessee Bridge that we could help with. So this series will show the collapse. Unfortunately, the node of interest, or the panel point of interest, is just off camera view, but you can clearly see that it initiated to the right of the photo and then led to the total collapse of that span. So I'll scroll through a couple of these photos. You'll see them come across your screen at that time. So what was going on at that time was the contractor was doing some resurfacing of the bridge deck. They had milled off portions and were putting back portions of an overlay, concrete overlay on the bridge deck. During their work, they had stockpiled supplies for their overlay, and with some detailed analysis, both by the NTSB and by ourselves, we were able to determine pretty accurately what loads were on the bridge at the time of the collapse, and took a look at what the gusset plates were as part of the design check to see why we thought the structure collapsed. And interestingly, in this figure, you can see that we have the U10 gusset plate and U11 gusset plates were a ½ inch thick, and just by comparison, a kind of a balanced look, the U6 and L7 gusset plates were 1 inch thick. But doing just some simple hand calcs, given the shear demands on it, we see that the U10 gusset plate just didn't have the capacity. It was about half its size. And when you look at the loads that were on the bridge, which were almost equal to the design load of the bridge at the time of its failure. So just goes to show you that for 40 some years, the structure didn't even see anything close to its design load. But when it did see that, it led to a failure of the gusset plates at the U10. So again, the cause of this structure was an original design error, and the U10 gusset plates led to the collapse of the I-35W bridge after it was loaded to approximately its design load. And lastly, I'll touch on the Prosperity pedestrian bridge, which was down in the Florida International University, University City in Florida. So this was a structure, again, under construction. Fortunately, it led to 6 fatalities and 10 injuries. So this was the planned bridge look. This was rendering. So it's 2-span truss, 175-foot main span. The pylon and the stays are actually decorative. They were architectural features, but didn't serve a structural function. And there was also a canopy that was to be placed on top of the structure that was part of its structural system. And most of the diagonals shown in the figure are post-tension. So this structure was being built using accelerated bridge techniques. So it was constructed essentially off-site and then moved into place on its main piers, and then with the additional spans being added, but they wouldn't have affected the main roadway under which the traffic was passing. So just to orient it, there's a couple of key members that were affected or were led to the investigation. There's the member 12, which is the vertical, and member 11, which is the diagonal, and then the deck. So just a slight high level timeline. So structure was started to be constructed in 2017 with the deck. The shoring was removed, and there was some cracking that was detected and some heard popping. And that photo on the lower left shows that initial cracking put together by some of the photos. One of the more obvious ones I think people have seen is the chamfer crack, which was observed, but it also looks like there was a sliding or a crack along the construction joint between there. The span was then moved in March using some specialized equipment to move it into its place. It was then additional cracking started to develop. And in the process of trying to evaluate that and to deal with, there was some retensioning done of member 11, which was the diagonal. And then you can see in the photo in the lower left or lower right, excuse me, you can see that the cracking got extensively worse. So clearly something was going on with the structure, and it essentially had failed, but had not collapsed. And so unfortunately it did collapse, and that led to the deaths and injuries. So if you look at kind of where the damage relative to the critical elements with the failure, you can see the node 11 or the member 11, which is diagonal, and the 12. And you can see that the lower end of the member 11 is missing in the photo on the right. It kind of had explosively blown apart. It also contains some blunt conical shape of the failure surface at the lower end of 11. And then 12 is the failure 12, which is the upper member there, is consistent with rotational effects of the member during the collapse. So one of the things we had to look for was just to evaluate, well, was this designed? How was it designed? What was it designed correctly? And so we did a code evaluation of the member 11 and 12. And we considered the area in green as the whole interface surface, because that would be consistent with how the member would, if you were designing it, how you would look at it. The AASHTO code, which is the governing code for bridges in the US, doesn't address the kind of compound failure mechanisms which ultimately occurred. So this surface which we evaluated really wasn't the final failure surface, but if you were designing, you would have probably approached this in the sense of looking at that entire surface. And also AASHTO allows us to take in the cohesion factor, kind of an aggregate interlock type behavior. So we looked at that in conjunction with all the stirrups and other bars passing through the failure plane. And if we run that check, we see that if you had properly roughened the interface surface at an area shown in green, you would have had a demand to capacity ratio or capacity to demand ratio of something greater than 1, which suggests it would have been appropriate and adequate. And then if it had not been roughened and you couldn't rely on some of that interface behavior, then it clearly doesn't work. So that pointed to the condition of that roughened surface as a primary factor in this behavior. And the Federal Highway, and it's part of its investigation, had identified that there was on the failure surface that there was no evidence that the surface had been intentionally roughened, and that it was just the original as cast surface of which the other members were then cast against. And so again, that was an important finding, and we wanted to understand a little bit more about that. So we actually cast some full-size specimens shown there in the yellow highlight as to what we were testing for, and we were looking at that construction joint and the effects of roughening on those. There's a photo of the construction joint being cast in the lab, and we can see just from the surface roughness features that the specimen covered by the NTSB gave it at a 0.76 millimeters. As we placed it, meaning just as cast surface, we came up with 0.94, and then when we intentionally roughened it, we ended up with about a 2.16. So the photo down on the left is the as cast specimen 3. The one to the right is the intentionally roughened surface. So those specimens were then taken to, there was an intentionally crack applied through that surface, so they were pre-cracked. Again, looking at the evidence of from all the photography taken of the cracks, we could see that those surfaces had already cracked. So they were pre-cracked, and then they were tested in test machines to look at their resistance. And again, if you start to look at that, you can see that the roughened surface, based on the loads calculated on the actual demands, you can see about 149% of its increase in capacity. So clearly the roughened and non-roughened makes a difference in the behavior of the structure at those connections. So conclusion would be, from our conclusions, if the construction joint was roughened as required by the project specifications and was again confirmed, and those would be, the Florida had specifications on what proper roughening was to create amplitudes to remove the latenance of the concrete, then this collapse would not occurred. Now we have to point out that this investigation was also done by the NTSB, which is our agency in the US that looks at transportation related failures. And they took exception to this opinion, and they attributed it to purely a design mistake by the designer, and that they just didn't have enough capacity. They had not, they didn't believe that the roughened surface affected it, though in our opinion, it was clearly demonstrated that if the roughened surface is there, then there's capacity. So with that, you can kind of see, if I start to walk through these, you can put the causes of failures with inadequate maintenance. And I think it was shown in Professor Nuti's talk that, that it's a wide group of failures that include that. The Schoharie Creek was one of undermining or scour, and after a result of this one and several other structures that collapsed, the Federal Highway began looking more closely at scour prevention and scour inspection. So that was one area where we've now addressed through additional inspection requirements as a result of these failures. The Tennessee Bridge failure to maintain stability during construction. This is an ongoing type problem that we see still today. The Bay Bridge was one of a series of vehicular type impacts. In this case, it was a fire impact as a result of vehicles, but we've had barge impacts and so forth that have dropped structures. The 35W Bridge was a design error, unfortunately back from the 60s, that because of the conservative nature of our bridge designs, we hadn't ever seen its design load at that point, but when it did, it unfortunately caused a collapse. And lastly, the FIU, we attribute it to construction error in the sense that the roughened surface was not properly created and led to the failure of that connection. So if I circle back to the I-40, well, what would happen with that one? Well, this one was interesting. This structure was built in the early 70s, which predated the requirements that I talked about at the beginning from the Silver Bridge of special fabrication requirements and inspections. And so this bridge failure had a weld where the failure fracture occurred that I showed in the picture. And they had done some weld repairs as part of the inspection process during fabrication. And those weld repairs unfortunately developed some hydrogen cracks shortly after their installation, and they were missed. And unfortunately, they were missed multiple times, including clearly visible cracks that have been detected by and shown through photographic evidence by passerbys that were there. And so that this, well, unfortunately was a failure of the system to properly detect a visible crack as part of our routine and bridge inspections. But it did show, though, that there was some redundancy and some ability when it was detected to stay up, so it didn't collapse. And the bridge was subsequently reopened, as I said, in May or in August. So what can we say out of this and kind of summarize it? Well, the design inspection practices following the Silver Bridge collapse have been very successful. And if you notice that there's not been a brittle fracture or fatigue related collapse of a bridge in the United States since that time period. So with the efforts done in that targeted area of structures, we've proven we can keep those structures from failing. Now, we've had fractures, as I just showed in the I-40 bridge, but they haven't led to catastrophic collapses. We still seem to have a problem with bridges during construction and obviously by impact. So that's an area that, you know, if we want to put our efforts and our focus, maybe we need to look at better requirements for contractors to provide stability and better erection plans, and then ways to protect our structures from vehicular impact. And then lastly, you know, we want to make sure we get to the bottom of the causes, because we can be very reactionary at the beginning. And if it doesn't address the problem, then we're just spinning our wheels and not addressing the long-term behavior of these structures so that we can prevent cracks. And with that, I am complete.
Thank you very much, John. Now we can open the floor to the discussion. Salvatore, I don't know if you selected some question. We can do it now.
Yeah, I've been looking at the Q&A, and there are like a few questions coming in. We still have time, and I think we can open the floor to the debate. So there is one. Let's start from Camillo. Be ready to be unmuted. One is a simple, probably yes or no question. Is, did you create a structural engineering model to reconstruct the failure mechanism of the Morandi Bridge?
Well, I can answer. We had 1 month, and obviously in 1 month we have a track of 2 of documents to investigate, and therefore we didn't create any model. There was some people that try later to create a model, but you should create a model capable of following the aging, first the construction, and then the aging. But if you enter in the details of the bridge, you find such a situation with cables which are not injected, corrosion, pitting corrosion, and the works on the for maintenance that they were making hole on the beam without checking, and so on and so forth. That I still think that a model is just a model, but then what's happened is different. And in fact, until now, there is the judges working on the subject, and they are discussing, and there is no idea. It is a matter of fact that the failure happened, and there are many aspects for the commission. And still, I think what we wrote at the end of the report is still valid. That there are various situations which are unacceptable. Totally unacceptable, because of our scarce knowledge of the corrosion situation. The people, the younger maybe, should know that the studies about concrete corrosion started around the 60s and the 70s, and the first PhD published paper on the subject are around 1970. So it's relatively young problem, and we have few structure which has in concrete or on press concrete which have more than 50 years. So you can study, but you do not have the real knowledge of the situation. So we are ignorant, and we must take some provision for that. At a certain level, you must understand that you cannot know more of what you know, and you must take some provision to be safe. That's our conclusion at the moment. And then in the future, maybe we will find something more. But to build a model, I don't know what you mean. A non-linear entry in steel degradation, corrosion, and so on and so forth, taking into account the lack of injection and so forth. So it's huge. It's a huge problem. There are some publications on that. I do not believe very much in those. There are in the report, in our, but also in others, the reconstruction of the failure sequence, and there are alternative possibilities, starting from the stays, or starting from the beam, or starting from the half joints, and so on and so forth. So all those are valid. There is no movie, a real movie, at least at the moment, unless the judge in its secret things has, there is not a real movie with the description of what's happened. There are very, very bad movies. They are published also, and so that's my opinion.
Thank you, Camillo. Picking up from your answer, you said that we are ignorant. There is another question. Maybe John can give his perspective. And Al-Somiri, he says that many collapses, many of those shown by John, I would say, are triggered by local deficiencies and also by unknown conditions, I add. So the question is, and many structures seem to have a very low redundancy. So shall we learn that probably we cannot solve the problem with safety, and we have maybe to try to be resilient, let's say, address redundancy rather than other aspects? John, what do you think based on your experience?
Sure. So yes, that's a observant point, is that many of these structures were non-redundant structures. So their failure of an element led to their collapse. Obviously, the reason those structures were selected was they're pretty efficient in the way we use our design. The design was efficient. And so to be cost effective, we optimized the designs. So it's a trade-off in the sense of, can we develop inspection strategies, maybe installation of certain sensors to help mitigate that problem in the future, or do we design the structures which may be less efficient in terms of dollars so that they have this redundancy built into them? And that's really that's a policy type decision as to how we want to go. Clearly, we can design bridges that are non-redundant, and we can design bridges that are redundant. There's a cost difference, and so that's really what the decision comes down to.
But what is in the US at least? What is the trend? I mean, after these collapses, do guidelines change accounting for this or not?
So the trend in the US has been there's not many trusses left because of the truss problems, and I-35W led to a lot of removal of truss bridges because there's requirements for additional inspection, hands-on inspection, meaning you have to get very close to the structure. So departments of transportation have decided that it's not worth their time, so they will remove those structures from their inventory, and when it comes time to replace them with new structures, go with structures that are redundant. So that's generally been the trend in the US, is to replace existing non-redundant structures with redundant structures.
I have a comment / question on this, and I see like a parallel between the Morandi Bridge and the Florida Bridge, meaning that we are mostly used to look at redundancy and fracture critical members in steel. Now we have two bridges that, like, Camillo was doing like a very good job, like not giving like a direct cause of that failure, but there is like concrete elements, the cable in the Morandi Bridge and the connection of the trusses at the Florida Bridge. And and I'm also interested in figuring out what the role of engineers is, because we have both cases in which the field observation was showing that there definitely was like some cause of like alarm, both for the Morandi Bridge because of maintenance of the cables, and there was like one of the pile, I mean the other pile of the viaduct was repaired previously because of that issue with the cables. And Morandi himself knew about the fact that there was some long-term behavior on those pre-stressed cable for like a single cable for a cable stability, where could be an issue. And then in the Florida collapse, there were some major cracks in the field, and people were re-stressing tendon, like bars around those cracks. So this is a long thing, but I would like to hear from you what you think about, like, first of all, the redundancy in concrete members and the use also of like details that are typical of like steel bridges in concrete, and also like the role that we play when we are called to make a judgment of what's going on in the field.
May I? Yes, indeed, we have to think to the date in which the Morandi Bridge was built. It was 1965 to 1967, his inauguration. In those periods, the cable-stayed bridge and all the bridge had just few redundancy, because we were not able to make calculation of complex structures. Nowadays, it's so easy because every young students have a powerful, even though he doesn't know, computer with the capability of 1,000 of unknown. But in those periods, and I was one of the engineers still working in that period, it was difficult to have also 3, 4, 5, 6 unknown. So the choice of Morandi was very clear. Few unknown, because you must understand the behavior of your bridge. Nowadays, nobody build a cable suspended bridge with the 3 suspension cables. And we know very well that we have many stays, and every stay is quite, in general, is doubled in order you can maintain, you can have a substitution. So this is obvious. Something is obvious because the technology in construction, in calculation, in materials has changed. But there are constructions that belong to that period. So we have to understand what shall we do with those masterpieces. In that case, we should have been cautious. That's what I'm saying. I'm not criticizing Morandi, because indeed he, after a few years, told to the owner, to the gestor, pay attention because the Polcevera Valley is very dangerous. There is a lot of corrosion, so you must be careful. This was 1982, if I remember, 1981. So he knew. But even when people built the Gothic cathedral, that was wonderful, they did not know if they were standing or not. They tried, and many of them are still standing. And so I wouldn't enter too much in this discussion. Do we need a complex structure? This was a mistake or not? Obviously, we know very well that if you make a redundant structure, if it is ductile, just if it is ductile, because if it is not ductile, there is no redundancy because you have failure which are brittle. But if it is ductile, it works. Otherwise, don't. So I think that, every case should be understood. That's my answer, and we must be very careful. We must be engineer, I would say, not calculate. It's not calculation the solution, is thinking and understanding.
There is an interesting, well, I think it's an interesting question from an Italian engineer, and I understand the question. He says, for John, is there a multi-risk assessment envisaged in the current American legislation? The question, I think, comes from the fact that the guidelines that Professor Nuti presented, that the recent guidelines that were issued in Italy, have a multi-risk approach. They consider hydraulic, geological, and seismic aspects altogether to rank, let's say, the risk of a bridge. Is there something similar in the United States, or how priorities are defined?
Yeah, I don't think we have anything that I'm aware of that's comprehensive like that. As we design these more signature bridges, these get incorporated into the design requirements such that a multi-risk assessment is done. What we have done is, in essence, have looked at inspection risks. So how often, the frequency that we need to do based off the structure and its perceived risks, either its deteriorated condition or its design or its exposure. And so I don't think it's quite as formalized, but we are, in essence, doing that through our inspection process, by the way that, you know, we're now evaluating bridges differently than we did, 10 years ago, in the sense that we now have, we're looking more at the reliability side of our inspection needs.
Salvatore, do you want to ask a question? I mean, in the list, because the list is very long.
It's very long, which is a great thing, and we don't want to just ask our own questions here.
There are several questions on monitoring, actually. What is the best monitoring, let's say, approach or inspections? Several people are interested in aspects like this. So what do you think, Camillo? Is there an answer to this question?
So if monitoring is important, you mean? I think is basic, but is like for the doctor with the people. If you make an earth check, but if you have the cancer, it's totally useless. So what you need is a good engineer that understands what is needed and then understand what he is going to prescribe for the monitoring of a structure. This is my basic thinking. By the way, nowadays the development of techniques is going on. I read, for example, there is a question of a person that indeed I know, but who is surprised as the rimmed method is still used. He is asking why. Is there some work? In fact, he is right. The rim method is used in test in comparison with others to understand how much it is reliable. So there is no method, indirect method, which is absolutely reliable. Every method has some uncertainty, and we must know, and he is right, that we must understand what we are doing, comparing results and understanding what we are doing. I totally agree. When I say we are ignorant, but engineers are used to tackle with ignorance and solve problems. If you don't understand something, you try to put it apart, solving the problem. If something is fragile for shear, you must reduce shear. You don't risk. So this is my position. I think we have to work hard to understand and develop the various things. There is another question I've seen on artificial intelligence. They ask if we are using, we are developing artificial intelligence for structural health monitoring. What I would say is, yes, we are working on the subject. Then we know that we need an engineer that understands something even after using artificial intelligence. That's
sorry.
Please, I finished. Yes.
John, do you have a different perspective? What do you think? I mean, I work on monitoring, and based on your presentation, I had the impression that, of course, we need to acquire information, but maybe on different things, because maintenance, I mean, degradation is one aspect, but many of the examples that you presented were things that with monitoring you cannot detect. So what do you think? How do you see this situation? I mean, shall we spend our money on other types of information?
Sure. So, yeah, I think in our experience doing a lot of monitoring, the idea that you're going to place sensors on a bridge and know where the problem is in order to detect that problem 30 years down the road is a pretty tough thing to be able to predict and do. And so if you actually know where the problem is, and then as Professor Nuti says, then why don't you just make your design or modify your design to address that problem from the beginning? Obviously, there's points where we end up an existing structure ends up in a position where it needs to be monitored so we can understand what's happening to it. And I think there's a good use, and the technology is advanced very quickly and allows us to really get a good understanding of what is behaving. So there's the balance of saying we're going to just put sensors on a bridge and not have to look at the bridge again, and the sensors are going to tell us when the problems arrive, is probably a little bit a reach right now, and whether that's using artificial intelligence. If you just look at the Florida bridge, clearly we had some people who observed in person cracking that was going on and just didn't understand the significance at the time. If we could expect an AI system to do that exact same thing, we have a long way to go before that can even happen. So I think monitoring has its place, and it can be used very effectively, but it can also be used and give us either tons of information that's not very beneficial, or just gives us a false impression of what's going on with the structure.
May I give a comment, Maria Pina, because I think that when you are speaking about monitoring, you essentially think to movements or something which is in movement. So measuring displacement or small displacement on strains, static or dynamics, but there are many things that can be monitored. For example, corrosion, for example, other things. And so when I'm speaking of monitoring, I'm speaking of everything that should be checked. And there are a lot of new techniques. It's like for doctors. The doctor, there are some that when you go to the doctor and you have a disease, send you to make 1,000 analyses, and maybe one is okay, all the other are rubbish. And the same is on structure. And now many engineers and many managing groups just ask you a number of tests. And you go there with 1,000 tests, and this is okay. You did 1,000 of tests, but maybe you didn't think that just the only one that was needed, as John said before. So I think that before the test and after the test, you have to enter in the data. You have to look at the bridge. You have to look at the design. What's happened? What's going on? Like for men when they have a disease, I think it's absolutely the same problem.
Sure.
One follow-up type of, like, want to hear your opinion on this. I mean, in the United States, like in the 70s, and this kind of like building on a question that I've seen, they start like this national bridge inspection system in the 70s, following those failures. Italy, maybe they're updating guidelines for more recently because of this collapse. You know, the focus today was on larger bridges, but you also both Italy, the United States, and everywhere in the world, we have a large inventory of smaller bridges that are like kind of close to need to be replaced and all that stuff. Would you, on the two sides, I would like, the question to John is like, do you think the system that we have in place now to manage our inventory in the United States is up to date? And Camillo, since Italy is catching up now, do you see any good ways of like handling the problem of how to manage the inventory, also how to train people to inspect bridges and report about those?
So to answer your first question, Salvatore, I think the US is moving in the right direction with its reliability and risk assessment, in the sense that I want to put my resources, if I'm a bridge owner, into the structures that have the potential for a problem, and not have to spend dollars on a structure that was just built 2 years ago and is essentially brand new. So if we target our inspection and what activities we do for those inspections, whether they're actually putting your hands on them or just looking to make sure that nothing's changed on the gross behavior of the structure, I think that's a cost-effective way. And I think we've proven that we can find problems and prevent issues from occurring by doing that approach.
Yes, really. Thank you for the question. I think we all have a problem. For example, as I try to say, in Italy, we have around a total maybe 1 million bridges, but the big one are 40,000. Not the big, the important one are 40,000, and so the other part are small bridges, but there are so many. So what we are going to do now is to make a big data bank at the Ministry of Public Works, where all the bridges, all will be put in. We will have in, I don't know how many years, something that will tell us everything of all the bridges that we have. But obviously for the small bridges, I think the problem is very big. It's like for people. In Italy, we are 60 million. In the United States, you are 350 million. And we do not check just a couple, the president and some others, maybe the engineers, but all the people are looked after. So we go to the doctor. So we need that everybody, every bridge must be checked. We don't have the money to do everything, but we must organize something. And as John said, we must prioritize and teach the people to make things. And for the new small bridges that will be much more than the big one, I think we must think about, for example, there is a strong push towards the UABSE, the integral abutment bridge, to reduce the number of joints in the small bridges, at least, because these are some of the points where you have problems and so on and so forth. Then for every bridge, a designer should give the criteria, and now is a must in every design, at least in Italy, but I think also in the United States, where during the life of the structure, you have to put your attention more to maintain the bridge.
Maybe we can shift a bit the focus. There is an interesting question here. More than a question, is a statement. Ilona Harrell says that the lesson learned should also be, integrated by a wider discussion on independent checks, allocation of responsibilities, adequately qualified supervisory staff. So it's not just a technical problem, it's a management problem also. Do you have comments on this? Do you want to?
Well, I know especially as we get into more signature type bridges, larger bridges, there's now requirements for separate independent checkers, and which hadn't been generally the practice in the US. I know in Europe, it's been there for a long time. So we're trying to at least make sure there's no gross errors in bridge designs as we go forward into the more routine structures. There's more emphasis placed on the quality control and quality assurance checking within the design. So I think those are there to help minimize the design side problems.
Yeah, if they are done.
Well, now they're generally, that's a mandatory requirement for if you're designing structure in the US, you're going to provide an independent set of calculations for the structure, and that'll be somebody who's developed a totally different model, a different. Oftentimes, they're different firms that come together as part of the design.
Yes.
Camillo, do you want to comment on this? Or?
Well, I think this is a very good question for the new bridges. But I think, for example, in Italy, we have, let's say, 1 million bridges. We have more than 40,000 big bridges, important bridges. The new one will be some percentage of those. So the big issue is on what is existing, not in the new ones. And so in what is existing, what do you mean for independent? Maybe for an independent check of the interventions, and yes, this may help. I agree. I think that what is very important is that we develop a culture about maintenance of existing structures, which is a total novelty, at least I think all over the world. We are very good for the new structures, but now we face with the problem that the big part, or at least in the developed country, the big part of the infrastructure is there. And so the big issue is to maintain in a reliable and sustainable way, I think. And this is the novelty. And so we have to learn to work hard to develop new techniques. There is a lot of things to learn and to do. And this is very interesting and very important for the young and also for the old, like me, for example.
Yeah, but I think that the management aspect is not necessarily related to new structures, because you have to manage maintenance. So it's the management in general that I agree with the comment is another important part beside the technical aspects, because of course, if there is a lack of management, any technical innovation or technique, is not very useful.
I have a policy question, and I want to kind of build on your experience, John and Camillo, on who are the subjects that you are involved when there is a bridge failure with or without fatalities. And I want to kind of hear your opinion on what you think with the expanding responsibility from the private sector that is often can be driven by financial input in their decision? How do you think we can make as an industry like a contribution to make sure that even if you're, you know, design, build, during construction, and also when there is maintenance, that it's in the responsibility of like a private owner, how we can provide guidelines to make sure that these things are not like, that we are listened when there is an issue with maintenance that is not properly done.
Agree, John, you want to start?
Sure,
Or
I mean, I get, that's fine. Thank you, Professor. Really, the idea really comes down to the contract documents, in the sense with if an owner is going to relinquish that responsibility to a design, build, maintain kind of contract, then the documents have to be very clear as the expectations in the design and in the maintenance of the structure. And I think we've found through some experience in the US that maybe the first couple of these, as they were released, it's relatively new in the US, probably weren't as specific and detailed as the expectations. But with some advanced understanding of these contracts, I think we can now structure them so that the owner at least gets what they want out of it. And I think that's really, the engineers will do what needs to happen. It's just the question of what's the emphasis and goals of the owner is to achieve what they want.
Yes, thank you very much for your question, Salvatore. I think this is really the basic point, and the experience of the Morandi Bridge, and not only, but in that case, is a very representative case. Indeed, this, I don't want to be too hard, but the ethics part of the problem is very important. And when the money becomes the only things to count, then there is a problem. There is a big problem. This is a big issue. For example, in that case, somebody says nobody checked, and maybe this is true, but it is clear that they, in that case, why they didn't intervene on the bridge, because the cost was very large, and there was the idea to build a different road that could reduce the traffic on the bridge and let the work on the bridge become simple, passing somewhere else. And from the economical point of view, it could have been a good idea. In any case, the contract between Autostrade and the state, the owner of the bridge, was done in a special way such that they probably could have some better revenue, not intervening or creating a big problem with respect to solving the small one that happen every year. And this is a complex issue. This is a very so you need that the checker become very expert. And on the other hand, sometimes this is not well considered, because to check an existing structure is so difficult, and to enter in these inspection sheets and reports is so difficult, and the number of bridges is so high that you need a lot of people and you need a lot of money to follow everything. So there are some ethical issues which are very important, and we know very well that to be an engineer, first of all, needs that you have an ethic very strong, like for every professional. This is the basic of the profession, at least in Europe, but I think also in the United States. And then money is important, but never before safety. And this is not for everybody. There are many movies on the stock market, for example, well, people buy the industry and they go in disruption because they make money on the stock. So this is ethic. So we could discuss, so it is the same problem. It's a very difficult task to be touched.
Thank you very much. Maria Pina, how much time do we have? We can stay all day here?
We are late 20 minutes.
Okay, so I think, I don't know, I think it was a great event. I hope people enjoy. We have a lot of questions here. I don't know if there is a way to get this question answered.
Brenda wrote to pose the question, and if we are unable to respond now, we shall try to respond later. So this is what she wrote.
Should we close?
Thank you very much.
Yes.
So,
thank you to you, to both of you. It was many people also confirmed it were two great presentations, very interesting, and also we had 200, more than 200 people present, and now we have still 130 people here. A lot of questions, so I mean, it's not just my opinion, it's well shared by many. Thank you very much from my part as well.
And like I said, we said at the beginning, this is the first of this series of Duo webinars. So if people that were participating have additional comments and they want to maybe see like a discussion, similar discussion about another topic, feel free to reach out to IABSE and we'll be happy to do a follow-up to this event. I want to thank you, John and Camillo.
Thank you.
Of course, Maria Pina for putting this together, and IABSE for hosting us. It was great. Thanks.
Sure.
Have a good weekend.
Thank
It's a
you.
weekend
Thank
for
you to
everybody.
you.
Thank you very much. Thank
It was a
you.
pleasure. Write us an email if you want. Thank you. Bye.
Thanks.
Bye. Bye. Bye.
Bye.
Bye.